Thank you for that warm welcome. It's good to be back in this visit to San Francisco. I'm told the sun was out a couple of days ago. Is that right? The rain is, plants need rain more than we do. Thanks for coming out for this. I'm here to just kind of talk about the universe, but through the lens, I'm restricted to the universe in my subject matter. In Death by Black Hole, first, I couldn't resist that title. There's a chapter in here with that title, and that chapter bears that title because it's a complete discussion of how you die when you fall into a black hole. And when I think of black holes, I think of sort of the adult counterpart to what, as a kid, would be T-Rex, because every kid loves T-Rex. But why do they love T-Rex? It's because T-Rex can eat the kid, all right? And you tend to have a deep respect for things that can eat you. So black holes, when you come too close to them, weird things happen to your body. And I'll get back to that in just a few minutes. I'm not going to read from the book because you can just get the book and read the book yourself. So presumably you came to hear me say something differently enlightening or even relatedly enlightening to what's in the book. And so what I'm going to do is, the book is organized into sections with multiple chapters within. I'm going to pick one of the chapters within its section that happen to be one of my favorites, and then I'll just kind of give you some summary points of those chapters, okay? And then, so this will be a sampling of the science that titillates me, but also, this collection is the science that has been most requested by the public. Even if I didn't think it was interesting, the public thought it was interesting. I said, well, let me find out why. And part of it was this black hole thing. Everybody wants to know about black holes. If I'm on the plane and someone sees I'm reading some astrophysics literature, say, what do you do? I do astrophysics. First question is, tell me about black holes. Then maybe Search for Life and Big Bang. And I'm trying to think, well, suppose I said I was nuclear chemist or particle physicist. That would just end the conversation right there. But they find that I study the universe, and it becomes this very engaged conversation. So there's this appetite for cosmic content for which I see myself as a servant of public interest. And so the material that's in here is the blending of aspects of the universe that I want to bring you to, and aspects of the universe for which I know the public has a deep curiosity to learn more about. And so that's how that goes. And let me lead off with the following datum. There's about 6,500 astrophysicists in the world. It's not very many, actually. It's just, a few thousand. And there's about 6.5 billion people in the world. So if you divide those two numbers, you get 1 in a million. So, no, what I mean, now the point of that exercise is, if you ever find yourself in the company of an astrophysicist, that's your chance to ask the question. Because you never know when that's going to happen again. That's just advice, okay? And I think that's why, like I said, I'm on the airplane, that people just bust out with questions. Like they've got some question center within them, and it's building up, and they're ready to explode, and the whole rest of it. So, that's just so you know. Okay, here we go. What I try to do here is connect the reader to the universe in a way that allows you to become a participant in the machinery of the cosmos. So I like to think of this book as your way to go around the back door and lift the hatch and see the gears turning and the oil box and the pulleys and the levers and all the things that allow you to understand not simply what's in the universe, but how the universe works. And in that way, you're empowered to have fresh thoughts about what's going on, rather than just repeat the factual information you'd otherwise get. And that's the goal of this book, okay? And I invite you to share in that goal if, in fact, you value that level of intellectual diversions in what is otherwise your workday. So I've got a chapter called Coming to Our Senses. And I'm told I have like half an hour or something, right? Is that about a half hour? Happy to do that. All I want, okay. I'll give you a late pass when you go back to work, okay, if you need. Coming to our senses. There's a whole chapter called Coming to Your Senses. And what that is, you know we've got 5 senses, right? Touch, taste, smell, sight, hearing, thank you. Touch, 5 senses. And then occasionally you get the person who comes up to you and says, I have a 6th sense, okay? These are people who claim to know stuff that they wouldn't otherwise know, typically. It turns out if you take those people and put them in the laboratory, the 6th sense just simply goes away under controlled circumstances. So either the 6th sense is this shy thing that doesn't lend itself to investigation, or it just doesn't exist at all, and we've duped ourselves into believing you had this power. But what I want to share with you is the fact that modern science, beginning 20th century, began to invent apparatus that would measure things that are completely outside of your 5 senses. No capacity to measure it whatsoever. So that in fact, modern science has multiple senses, dozens of senses. So you want to ask, you have a 6th sense? Here's some things you can't measure. For example, the magnetic field in this room. The human body has no capacity to measure the strength of a magnetic field. The human body has no strength to measure whether we are being bombarded by ionizing radiation. You'd eventually figure that out as your limbs fell off, as you'd come to learn that this was the case, but while it was happening, you would have no idea. We don't have high-energy radiation detectors built into our system. We've got detectors that can do it. So if there's something emitting ionizing radiation anywhere around, we'd be able to find it. I call that a sense, another kind of sense. Now, not only can we go outside of our 5 senses, we can vastly improve the 5 senses we have. And so what science is about, of course, is advancing our capacity to intersect with the cosmos. That's what science is. So that's what a microscope does. You see smaller things you never know. The telescope, see farther away. Particle accelerator. All of this are simply ways to enhance and extend and invent beyond our 5 senses. The simplest ones among these are, there's visible light, Roy G. Biv, right? Roy G. Biv, remember him? Red, orange, yellow, green, blue, indigo, violet. There's really only 6 colors there, but Isaac Newton, who first labeled these, he had a fascination with the number 7, and he came up with 6 colors. I got to put in a 7th one, and so he slipped in indigo there. Doesn't belong there at all, but he slipped it in. If you're going to put in indigo, you might have put in 7 other colors, have 14 colors in the spectrum if you're going to be that specific. Indigo is this narrow segment between the blue and the violet. It doesn't, in that scheme, deserve its own color name, unless you're going to have way more than 7 to label. But that's neither here nor there. So those are the colors, and we define that as visible light, but light goes far beyond each side of that spectrum. You go beyond violet, you get ultraviolet. You go the other side of red, you get infrared. And you keep going in each direction, so violet, ultraviolet, X-rays, gamma rays. Red, infrared, microwaves, radio waves. All of this is light. It all travels at the speed of light, and we had no telescopes capable of observing outside of the visible spectrum until 1920, and that was a very crude telescope itself. And we didn't start really getting data on this until the 1950s and 60s. So we were practically blind to the universe before 50 years ago, thinking that our eyes were somehow the true measure of what's out there. So all of our detectors and telescopes were extensions of our eyes and not probes into whole other branches of what we call the electromagnetic spectrum. And so your senses are really these, they're good for, getting around the house, but they're not good for decoding the universe. And here's how they get in the way. There's something called common sense, right? What is common sense? Common sense is if I let go of this gavel, it will drop. So let's try that. Okay, it dropped. Now, so important is that fact to our senses that when you tell me to drop it, that's an instruction for me to let go of it. What you really should be telling me to do is let go. That's your instructions to me. Then it drops. Okay? Suppose we lived in a world where 30% of the time I let go, this would float up to the ceiling. Then you wouldn't say, just drop it. You just say, let go. And 30% of the time, it would go up. Now, it sounds like I'm just making this up to be funny, but no, there are parts of the universe for which the laws of physics as we experience them no longer apply. One of them, for example, is the branch of physics called quantum mechanics, where matter behaves in ways that defy common sense. Particles exist here, disappear out of existence, and pop into existence over here without any visible means of getting from here to there. A particle sits there, minds its own business, and then transforms into another particle of a whole completely different identity a split second later. This is matter behaving, not badly, matter behaving normally under those conditions. So, if I'm here and this cup of water disappears and shows up over here, we would say, that doesn't make sense. But if that's all you had known as a particle, you say, hey, that makes sense. So what you think makes sense has nothing to do with reality. It just has to do with your life experience. And your life experience may only be a small smidgen of reality, possibly even a distorted account of reality at that. So, what this means is beginning in the 20th century, as our means of decoding nature became more and more and more powerful, we started realizing our common sense is no longer a tool to pass judgment on whether or not a scientific theory is correct. And thus was born quantum mechanics, relativity, curved space, expanding universe. So when I tell you that the entire universe has been around and expanding for 14 billion years, you go back 14 billion years ago, the entire universe fit on the head of a pin, you're going to say, that doesn't make sense. And I'm going to say, I don't care that it doesn't make sense. The universe doesn't care that it makes sense to you. That's not its goal in life, to make sense to you. It issues forth from a whole other investigation of the behavior of matter of the large, Einstein's general theory of relativity. And then there's the shotgun wedding of the general theory of relativity, the theory of the large, with quantum mechanics. This is the physics of the small. The early universe, the large was small. And there's general relativity and quantum mechanics intersecting in a shotgun marriage. They're not otherwise compatible descriptions of the universe. This works there and this works there. Now they got to work together. We have no understanding of how they'll work together. We got top people working on it. They're called string theorists, okay? And they're still not there yet. They're still not there. They're working on it. Every time I ask them, they say, oh, we're a couple of years away. They've been saying that for 20 years. I've been asking them since the early 80s. But it's the only game in town, and they're very inexpensive to support. You give them a pencil, you say, here you go, and some paper, and we'll throw in a computer, and they're done, okay? So I'm okay with that. They're not going to bankrupt the science budget. And so in the exposition of coming to your senses, it's basically a celebration of what it is to have 5 senses, but then the reality check on the fact that our senses are not only feeble, they're inadequate to properly decode all that's going on in the natural universe. And so a prevailing theme here is an attempt to give a reality check to the urge that we have, the urge, understandable, but inexcusable urge that we have to think more highly of ourselves than we actually deserve. This is a theme that's repeated through the history of human assessment of our place in the universe. And in a little ways, it continues that way today. But some are sort of have enough foresight and hindsight to say, oh, I'm not going to make that mistake again. Here we are on Earth, and Earth is special because it's Earth, and the rest of that's just the sky. And then we find out we're one of the planets. And then, oh, well, surely our sun is special. No, that's one of 100 billion other suns in our galaxy. Well, the Milky Way, yeah, that's the universe. No, Milky Way is one of 100 billion galaxies in the universe. Well, if we're in the galaxy, we must be in the center of the galaxy. No, we're out somewhere in Nowheresville, okay? Leading completely undistinguished existence in an undistinguished quadrant of an undistinguished galaxy. Get over it, okay? Find some other way to measure your importance in life. Don't reference the universe. Why not help someone? That'll measure your importance, okay? That's how to be important. Help somebody else. Lead a better life. And so that's a running theme, by the way. I say that there, but every one of these chapters, there's some reference to it. And so let me move on and pluck another one from the, how much time, damn, I ate up all the time just talking about that. I've got a chapter called Vagabonds of the Solar System. That one's fun. I'm not going to dwell on that too much because in there we talk about Pluto. Pluto, has been on hard times, Pluto. And and it's interesting because, I had a little something to do with that. In the year 2000, our exhibits at the American Museum of Natural History, I and two colleagues of mine were co-writers of all the exhibits. We decided, upon noticing that Pluto, there are other objects orbiting the sun about where Pluto orbits. About the same size as Pluto, made of the same stuff as Pluto, same cockamamie orbits like Pluto has. And so we said, well, let's organize the exhibit so Pluto is with the rest of its newly discovered brethren in the solar system. And then the gas giant planets that put those together, they have more in common with each other than any one has with any other object. The rocky, smaller planets and the Mercury, Venus, Earth, and Mars, they have more in common with each other than any one of them has with anything else. So we presented the solar system as a collection of families. Well, page 1 story of the New York Times. Pluto not a planet? Only in New York. My phone was ringing off the hook. I was getting hate mail from 3rd graders. And I said, man, people feel strongly about Pluto. And most of the Pluto lovers out there, are there any among you in the audience? Pluto lovers? Raise a hand if you're a Pluto. We got Pluto lovers in the front row. Now, I'll bet you 10 to 1 that this will play out exactly as I know, okay? Pluto lovers, please raise your hand once again. Did you know that there are 6 moons in the solar system bigger than Pluto? Moons. He didn't know that. Earth, moon among them. Didn't know that. That's because the Pluto lovers have elevated Pluto to a greater significance than it actually is. It has grown in your mind and in your soul, but not in the universe. Okay, so Pluto, did you know? Not to mean to be dissing you in the front row here, but I had to get this. Did you know, sir, did you know that Pluto is more than half ice by volume? Which means if you brought Pluto in, let's put it just to, now you're not to bring it too close, just bring it to like where Earth is. The heat from the sun would evaporate the ice, turn it into gas, and it would make this long plume of a tail. Now, what kind of behavior is that for a planet? We have words for things with tails. We call them comets. Comets cross the orbits of other planets. So does Pluto. Pluto crosses Neptune's orbit. If you just add it all up, there's no way out of this. And I think the reason why Americans liked it so much is because we have this other association with Pluto. Pluto, the dog. Europeans don't care. I spoke to Europeans. They said, oh, we don't care whether it's a planet or not. Who cares? Because they don't have this dog legacy, this baggage. Do you know who Pluto is, the creature? Anyone doesn't know? Okay, Pluto is Mickey's dog. Now, I don't know about you, but that's disturbed me for a long time. Something's not right in the mammalian kingdom if Pluto is Mickey's dog and Mickey is not Pluto's mouse. There's something wrong there. A mouse owning a dog. Dogs eat mice, okay? So I want to understand, how is it that a mouse can own a dog? Then I learned that, so I called up Disney, and apparently, this is important stuff you gotta know. So apparently, if you don't wear clothes, you can be owned by another creature who does. That's how you can have animals owning animals, okay? So Pluto runs around butt naked, and Mickey Mouse wears that bow tie, and so that's how you get the social order of the characters. Well, meanwhile, it turns out that Pluto the dog was first sketched the same year that Pluto the object was discovered. So they both have the same tenure in the hearts and minds of the American public. And Pluto the object was discovered by an American. So there's this sort of importance of stuff Americans do getting into the thought equation about how you evaluate who and what Pluto is or should be. So anyway, there's a little bit of that in the vagabonds of this whole thing. But right now, it was so much. I have a file this wide that this month, I'm depositing a manuscript to my publisher called The Pluto Files. This is an exposition of all the hate mail and all the correspondence that I've had with people who are just pissed off about what we did with their favorite planet. Had to get that off my chest. Sorry about that. How am I doing on time here? Man, I got so much I want to do here. The universe is a big, it's like, here, you got 30 minutes, give them the whole universe. It's like, how am I going to do that? Should I tell them about the asteroid that's coming? No, I know. If there's enough time, we'll tell them about the asteroid that's going to hit. Okay. Good. If I forget, remind me about the killer asteroid that's due to come on Friday the 13th in April of 2029. But this only if I forget. Just remind me about that. It's headed for the Pacific Ocean, by the way. But I'll fill you in if we can. That's just the test. I'm going to wait till the very end and see how badly you have to get back to work, all right? It'll be. There's a chapter, excuse me, I'm recovering from it, chest cold. There's a chapter here called Goldilocks and the Three Planets. And this is simple. The idea is simple, but the consequences are profound. If you want to look for life in the universe, beyond Earth, how do you go about it? Well, you have to kind of define life, but you only have an example of one. Biologists celebrate the diversity of life, but behind closed doors, they lament the fact that they only have a sample of one, because all life on Earth has common DNA lineage. And so, in fact, there is no biodiversity on Earth compared with what the biology would be to a completely alien creature. Then you're talking diversity, okay? So that's just that's that. So now, one of the things we're pretty sure life as we know it requires is liquid water. Carries nutrients around. It's very common ingredients in the universe, hydrogen and oxygen. So where would you have to put a planet so that it could sustain liquid water in its orbit around a star? You don't want to be too close because the water what? Evaporates. You don't want to be too far away, the water freezes. So it's got to be just right. So that's why it's like the Goldilocks thing, okay? You remember Goldilocks. That story disturbed me too. If I were the bear, I would just eat Goldilocks, you know? Sleeping in your bed, eating your food, you just maul her, all right? But that's not the story that they wrote. But surely that's what would have happened under those conditions. So anyway, so there's Goldilocks. we have a zone around every star for which these conditions hold. We call that the habitable zone. Too many syllables, I know. Forgive us for it, but we couldn't figure out what else to call it. Some call it the green zone, but the habitable zone. For our solar system, Earth is in the habitable zone. It's right there. Of course it's there. We have liquid water on our surface. But how about if you go a little to the left? Go a little closer to the sun. You get what's generally referred to as our sister planet. It's about the same size, about the same density, same mass. It's the planet Venus, a little closer to the sun. What's the temperature on Venus? What's its atmosphere made of? It's got a carbon dioxide atmosphere, 100 times the density of Earth's atmosphere, and it has a roaring greenhouse effect, a runaway It is so hot on Venus, it is 900 degrees Fahrenheit. I did the calculation. You could take 16-inch pizza, put it out on the windowsill, it'll cook in 9 seconds. Now, of course, you would have vaporized along with it, so it's not a thought experiment. I'm not inviting you to try that. Something bad happened on Venus. Something bad happened there to its climate. Some knob got turned. Let's look a little to the right. The next planet out from the solar system, from us, that would be Mars. Mars has evidence of once having running water on its surface. There are riverbeds that meander. All the visual cues that you see when you fly across country on the airplane and you look down, you see the Mississippi Delta, you see if there's a flood, you see the plane. All of these features are there, yet there's not a single drop of water left. Something bad happened on Mars, too. Something changed there. I want to know what that was, because today we are turning knobs on Earth, big knobs. Carbon dioxide knobs, environmental knobs. And it's, oh, Earth will be fine with it. I don't know that. I got a neighbor to the left, a neighbor to the right. Mars is bone dry, 200 degrees below zero. Venus is 900 degrees. I want to understand what can go wrong in the cosmos so that we can avoid that for Earth. And so Goldilocks and the Three Planets is an assessment of where conditions would give you liquid water and what would then drive your capacity to search for life. And that, for me, is one of the most fascinating of the modern frontiers of cosmic discovery. And briefly, we've learned that you don't have to be in the habitable zone to have liquid water. One of Jupiter's moons, Europa, is actually kept warm by gravitational stress from Jupiter itself. It puts stress on Europa. And if you ever played racket sports and you hit the ball, you literally at the beginning say, let's warm up the ball. You're actually warming up the ball every time you hit it. You compress it and it has a recoil force that bounces back. But the energy that you pumped into it, it's got to go somewhere. It's got to go somewhere. Some of it goes to pop the ball back into shape. The rest goes into heat, the intermolecular vibrations of the rubber of the ball. And so Jupiter is pumping heat into Europa. Europa's and Jupiter way outside the habitable zone, because you calculate the habitable zone based on sunlight. But out there, you got a heat source from Jupiter getting pumped into it. It is icy on the surface and liquid ocean beneath it. It has been liquid for a billion years. I want to go to Europa and go ice fishing. Cut through the ice, lower a submersible, look around, see what's there, see what swims up to the camera lens and licks it. That'd be kind of cool. Liquid water for a billion years. Imagine. Life on Earth didn't require that much time to form. Life on Earth, here's something you might not have known. It's a recent thing. We all took biology in school, I think, presumably. Okay? You took biology, and what did you learn? Well, when did the Earth form? Earth formed 4.5 billion years ago. What's the earliest sign of fossil life? Back then when we took biology, it might have been 3 billion years ago, maybe 3.2. So then you say, well, life had 1.5 billion years to form on Earth, okay? From the primitive chemistries of the early days to the complex chemistry of life. And that's pretty good because then we went another 3 billion years after that. But as time went on, we found earlier fossil evidence, not 3.5, 3.7 billion years. As time went on, what we found is that the early solar system was a shooting gallery of leftover debris slamming into Earth's surface. If you're going to do that, it's not fair to start the life clock because complex chemistry could not have begun if your liquid molten surface. So that's not fair to start the life clock then. Let that period of heavy bombardment, which is officially called the period of heavy bombardment, it's true. I've said this before, we tell it like it is in astrophysics, okay? Spots on the sun, what are they called? Sunspots, thank you. Dark areas of space, you fall and you never come out again? Black hole, see? We are into one-syllable lexicon. The origin of the entire universe, space-time, and anything? Big Bang, okay? Ask the biologist, what's the most important molecule in the body? It's deoxyribonucleic acid. 12 syllables or 10 syllables. Later, you get the molecule. So, where was I before I interrupted myself? Oh, thank you. Thank you. Somebody was paying attention over here on the left aisle. The period of heavy bombardment. Once we could do the computer calculations of how long it would take to vacuum up the remaining debris of the solar system to become the planets, we realized that took upwards of 600 million years. Earth didn't cool down until 600 million years after it formed. So you go from 4.5 billion years ago to 3.9. 3.9. Now you start the life clock. And when is the first sign of fossil evidence? 3.7. 200 million years to form life on Earth. That's nothing in the time of the Earth, and it's less than nothing in the time of the universe. So you have complex chemistry enabled by the ingredients of life itself: hydrogen, oxygen, carbon, nitrogen, other, the famous element other. Those are the top 5 ingredients in life on Earth. What's the top ingredients in the universe? Hydrogen. Yeah, we've seen that on our. Oh, next one is helium. But helium is not chemically interesting. You can inhale it and, sound like Mickey Mouse. But it doesn't bind with anything, so it's not useful to us chemically. Next in the universe is oxygen. That's what it was in the human body. Next is carbon. That's what it was. Next is nitrogen. That's what it was with us. Next is other, just like it was with us. So if we were made of like some isotope of bismuth, then you'd have an argument to say that we are something rare in the cosmos. But we're made of the most common ingredients with a chemistry based on carbon, which is the most fertile of all elements on the periodic table. You can make more molecules out of carbon than you can with all other elements combined. So you got the right ingredients, and you have the fertility of the carbon atom. You're there, and give Earth 200 million years, you're there. You're there. And so when you want to think about the search for life elsewhere, these are factors that come in. Just because you haven't figured out how to do it yet in the lab doesn't mean nature had a hard time doing it. That's the hubris again, okay? Just because you can or can't do something, therefore it is impossible that way in the whole universe. Got to be a little more humble about our ignorance and get top people working on it. And so, I had a point out of all of that, and I forgot what the point was going to be. Europa, thank you. So, here's it. So let's say we find, see, people on the left side of the room are actually paying attention. You guys over here, I don't know what you're doing, okay? Left side of the room, yes. So, Europa, let's say you find life. Here's an unresolved question, okay? We've got top people working on this without a solution yet. If you find life on Jupiter's moon, Europa, do you call it European? See, we don't have an answer to that yet. We don't know what to do about that, okay? I don't know. Just, okay. By the way, these are not just idle thoughts. For example, Because you want to like get the answer before it happens, so you're not caught having to make something up on the fly. If you're from Mars, you're a Martian, right? You're from Earth, you're Earthling. You know, we've heard that. You're from Venus, you're a Venusian. But it turns out the astronomers got there too late. We got to Venus too late, and we've regretted it ever since. Okay, Mars is the god of war, you remember from Roman mythology. Venus is the goddess of love and beauty. They called that planet Venus before they knew that you would instantly vaporize on Venus's surface, okay? Because it's beautiful in the sky, even those seething gases of carbon dioxide and sulfuric acid. Beautiful Venus. Anyhow, so we got there too late. We were beaten. We got beat. Why? Because the medical community started looking around, they got the microscope, they look and say, hey, there's this particular disease that a class of disease that only shows up as a product of lovemaking. We must name that disease after one who's accountable for this. That would be Venus, wouldn't it? Let us name these diseases venereal diseases. To be a Venus is to be venereal. And then, damn, we could. So at that point, we can't now call life forms from Venus venereals, right? Imagine the spacecraft land. Hi, we are venereals. It's like, nope, excuse me. Get somebody else to shake that hand. You know, so we had to then invent a new thing that is not derivable from the Latin, and so we just invented Venusian. But it really, they should be venereals, okay? So this is stuff that, all right, I have 30 seconds left here before we go to Q&A. But I'm not done yet. I said only after I'm done. And notice again, it's the left side of the room asking about the asteroid. They don't even care when they die, all right? They don't know over here on the right. All right, I should first describe to you how you die falling into a black hole. You ready? It's quick. I get this done like that. You ready? I got a whole chapter on it. I would tell you because it's kind of, because you should know this. All right, you standing up on Earth, your feet are closer to the center of the Earth than your head is. You can calculate that the force of gravity at your feet is stronger than the force of gravity at your head. Because the closer you are to the center of the gravity of an object, the stronger its gravity is. It's that simple. Not more complicated than that. But don't blame your lightheadedness on this fact, because that difference is very small, because your height is small compared with the size of the Earth. But imagine you're falling towards an object where your height becomes significant compared to the size of the object. Under those conditions, the difference in gravity becomes ever so great, like as you descend to the center of a black hole. So you take a feet-first dive, you'll begin to stretch. And that'll kind of feel good at first, right? We all stretch. Wake up in the morning, it's the first thing you do, stretch. And then you realize it's not stopping, okay? And you begin to stretch more and more and more, and you can calculate when the difference in the force of gravity becomes greater than the molecular bonding forces of human flesh. At that moment, your body will snap into two pieces, most likely at the base of your spine. Now, you'll be able to watch this, okay, because all your vital organs are above your waist. You have important organs below your waist, but they're not vital, okay? So you can just watch that. You watch your legs sort of descend. Then the upper part will feel the same effect as you get closer. So will the lower part. So they will then snap into two pieces. Now you are 4, and then 8, and then 16. And then you bifurcate your way down to the abyss. Now, it gets worse. Not only did you become this stream of particles, you are now getting funneled through the fabric of space. Because Einstein's general relativity tells us that gravity curves space. And in the vicinity of a black hole, you are funneled down to a point. So you are not only stretched, you are extruded through this structure, like toothpaste through a tube. And we have a word for this. It's called spaghettification. It's a real word. I'm telling you. And we're good at inventing words about how to kill people. When electricity was discovered and used in the late 1800s, 1900s, they said, hey, you can kill somebody with electricity. Let's invent a word for that. Electrocute, okay? So we're good at inventing death words. Spaghettify. You become spaghettified. And the Death by Black Hole chapter talks about not only how you'll die, but how black holes dine upon stars and gas clouds that wander too close as they get flayed of their outer surfaces. And I'll leave you with, I guess, you want to know about the asteroid. Okay, I'm going to take 2 minutes, and we go Q&A beginning Q2. How about that, sir? Yeah. You cool with that? I'm cool. He's cool, okay. This is the coolest guy around. He's just chilling here. And I got to give this side of the room a chance to redeem themselves, okay? So, December 2004, an asteroid was discovered. By the way, asteroids are discovered all the time. This is not a new thing. Hundreds of asteroids are discovered each year. And some years, thousands get logged. Brand new asteroids, new to our awareness. This one was discovered. They calculated its orbit. And we found out that the orbit would come dangerously close to Earth. And the uncertainty in the orbit was such that its next time around, it might even hit Earth. And if it hit Earth at the center point of the uncertain orbits, so in other words, you run the computer model, and there's a range of orbits it could have based on your data. And you get better data, then that range gets narrower and narrower and narrower. But based on the data available at the time, there's a range of orbits. Within there was a tinier range of orbits where if it threaded that keyhole, it would hit us 7 years after that. Why didn't you read about it when that happened? By the way, it would hit, if it went through the center of the keyhole, it would hit the Pacific Ocean 500 kilometers west of Santa Monica. I will describe the tidal wave it would make in just a moment, the tsunami that would be. Why didn't you hear about it? Because the week it was discovered was the week of the Indonesian tsunami. And so the odd thing, though, is that, right, the Indonesian tsunami duly grabbed the headlines. But if this asteroid hits, it would create a tsunami beyond measure. No, we can actually measure it, but beyond anything you'd ever seen, and would make the Indonesian tsunami look like the tide's just rolling in. And so we kept monitoring the orbit, trying to get a tune. And so here are the facts. On Friday, the 13th of April, in the year 2029, this asteroid named Apophis, P-H, Apophis. That's the Egyptian god of death and darkness. We didn't name that one Bambi, okay? It obviously got named after we saw where it was headed. So, and I'm not ignoring you guys over there. I'm just trying to bring them into the conversation over here, the right side of the room. So, Apophis is the size of the Rose Bowl. Imagine the Rose Bowl were like an egg cup, and then you get an egg to fit in it. That's the size of this asteroid. On April 13th, the year 2029, it will come close enough to Earth to dip below our orbiting communication satellites. It will be the biggest, closest thing ever to come to Earth in our recorded history. Recorded meaning when we took records of events and things. Now, the uncertainty in that orbit includes what I'm saying was called the keyhole. A narrow region within these uncertainties. If it threads that keyhole, it will hit us 7 years later, once again on April 13th. Although this time, not a Friday. It would be a Thursday that time. I'm pretty sure I looked it up. Thursday the 13th. You know, that would create a whole new legend of movies, you know. Thursday the 13th, you know. So, what you want to do is make sure it doesn't go through the keyhole. Now, you got some people out there, let's blow the sucker out of the sky, you know. These are the men who wield nukes, because they can justify your nuclear arsenal. But that's not a good idea, because you blow the thing to smithereens. Now all the smithereens are headed towards you. And what would have hit in just one spot now takes out half the world. So, plus you don't know where it's going to go. Bombs are uncontrolled releases of energy. That's why they're bombs, okay? So you want to be able to control what this thing does, and one of the things to do is to deflect it from harm's way. So we've got top people working on deflection scenarios. But when you deflect it, you've got to be careful because it's still there. You've got to look over your back. Next time it's around, you got to keep looking at it, okay? But if you have the power to deflect, you now have the power to not greet the same fate that the dinosaurs did 65 million years ago when an asteroid came and took them out, leaving them extinct. Because I don't want to be the laughing stock of the galaxy when they find out that a species that had a space program and the intelligence to stop an asteroid impact just simply went extinct. That'd just be embarrassing. I don't want, you know, it's okay for the dinosaurs. They had that pea brain and they didn't have opposable thumbs. They were not going to build a spaceship. So, it's called Apophis. I would think of it as a coming attraction on a continent near you. Let me just end quickly. It plunges into the Pacific. It'll go about 3 miles down before it then explodes, cavitating the Pacific in a 3-mile wide hole. So you now have a hole 3 miles wide and 3 miles deep. Water does not like having holes in it. So the act of having made the hole sent a pulse of water to the shores all around. Then the water fills in the hole with such ferocity that the water rises back up high into the atmosphere, falls back down, cavitates another hole. There goes another pulse. And this will continue for dozens of times. It'll go to the shoreline. The wave will go to the whole entire North American coastline, and the wave will go in, maybe about 1/4 mile. Then it'll get pulled back out to get ready for the next wave. It's not one of these one-way marching tsunamis like the one in Indonesia. This one goes in and comes out. But if you had a home here, the home comes out, gets taken out. But now the wave comes back in. In comes your home again. But it doesn't have the shape that it had before. It's now debris. And so the debris becomes this mulching machine, this sandblasting machine, this thing that ablates the entire coastline, wiping it clean of all traces of civilization. So have a nice day. Thank you for your... Thank you.
Thank you, Dr. Tyson. I remind our radio audience you're listening to the Commonwealth Club, a noon session with Dr. Neil deGrasse Tyson, talking generally about his new book, Death by a Black Hole, but more generally about current issues in astrophysics and cosmology. We have some time for questions. As you might see, if you've been watching, I have a fistful of questions here, and we will obviously not get to all of them, but let me try to get to as many as we can. First question is, there's a lot of discussion today about whether it's economically and scientifically better to pursue manned space travel or unmanned space travel. Could you comment on that question?
Sure. If I wear my scientist hat, as a pure scientist, I say, send the robot. Okay? Robots don't need to come back. You barely need to feed them, all right? And you don't have to keep them toasty warm. So robots are very low maintenance compared with human beings, if your goal is scientific inquiry. However, there's a whole other dimension to exploration that transcends science. There's the adventure, there's the urge to explore. If you look at the history of the greatest explorers, none of them were scientists. The science that got done as a product of their efforts were basically piggybacked their missions. And some of those missions had other kinds of motives, some military, some hegemonistic, how's that word go? Hegemonistic, some economic. And so there are drivers far stronger than scientific inquiry that moves money from societies to discover things. And so I don't want to be my read of history tells me I should not go forward with the naivete that you can just stand in front of the Congress and say, do this because the science is what we need. The history of funding major projects is a consistent demonstration of the failure of that as the sole driver for doing these kinds of activities. Not only that, there's just the practical matter. The MAN program is embedded in multiple congressional districts across the country with representatives that vote NASA's budget. So it's much more complex than just whether or not you're going to get a scientific result back. And when you factor in that full dynamic, you do both, because the last I checked, no one has ever named a high school after a robot.
The general battle between religious discussion around creationism and notions of Darwinism and origins of the universe have occurred in the biological sciences. Are you finding that physics and other cosmological studies are now starting to take up that debate?
It's being taken up a little bit. I have direct measure of that where I work. I work at the American Museum of Natural History. We have an entire exhibit on the Big Bang and the origin of the universe. And another part of the museum, there's like the Hall of Human Biology. But what happens is, if someone comes in saying, how come you don't mention God here? Where is, why not? And what I do is, I just send them over the Hall of Human Biology, where we have humans holding hands with chimpanzees. And then they never come back. Like, that was enough to completely derail the inquiry. So my read of concerns within the religious community, it is vastly more concerned about our near identical relationship with the chimpanzee than it is about whatever we say about the Big Bang. Mm-hmm. Now, I've been brought into some of that conversation just to help people understand what science is and what science is not. And so I think what's unfortunate about how that's turned is religion is becoming sort of the enemy of science, or science the enemy of religion. And that's only because religious forces are trying to put religious writings in the science classroom. Now, there's no tradition of the science professor knocking down the door of the Sunday school telling the preacher to put science in what goes on in the Sunday school class. There's no tradition of that. There's no scientists picketing outside of churches saying, equal time for Darwin. That doesn't happen. It's not how this country was founded. So it's this needless debate going on out there when people need to know if your belief system derives from what's called inspired truths that do not come out of empirical investigation of the physical world, it has no place in the science classroom. That doesn't mean it has no place anywhere else. Put it in the religious philosophy class. Put it in the history of human thought class. But it just has no place in the science classroom. And it's not about the First Amendment. It's about what is science and what is not. And that's where I'd put it. Thank you. Oh, thank you.
During your talk, you used the term thought experiment several times. Could you expand on that phrase?
Oh, thought experiment is what you do if you don't have any money, okay? If they declined your recent grant proposal, then you just do the thought experiment. The thought experiment is you're armed with enough sort of laws of physics, and you want to test them in some way. So you invent, in fact, thought experiments came into fashion in the time of Einstein, because Einstein was a theorist. And many of the famous Jewish physicists of the day were theorists because they weren't given money to be experimentalists. Many of those Jewish physicists were in Germany, and the German culture, the German philosophy at the time held that experimental science was the highest form of science you could do. And the theory was what laggards would be left with. That's the crumbs on the plate. So Jewish physicists of the day could not be experimentalists. So they were relegated to the backwaters of theory. And in fact, that is the birth of modern physics, the theoretical discoveries that came out of that. So Einstein, not having the benefits of a laboratory, would take an idea and see what the consequences of that idea would be by constructing a thought experiment. What would happen if I took a beam of light on a moving train? You would see this pattern if you're on the ground, but if you're on the train, it just goes straight up and down. So how can one person see this angle, but you see this going straight up and down? And out of this unfolds the theory of relativity. And so a thought experiment is basically how to get closer to nature on a budget.
We read about the new particle accelerator coming online in Geneva at the end of this year, and then there was an article today about a possible even more high-energy accelerator being built in China. What will be the contribution of these facilities to the types of problems you're thinking about?
Anytime you build a facility that probes nature in regimes never before seen, you're going to make a discovery of something. That's just the history of the field. And that's why we can say pretty much with confidence that if all you have is a tabletop, laboratory tabletop, you're not going to discover a new law of physics there. You're probably not, because you're not at the limits of the regime. We've been there already. We're done with that. Take me someplace I haven't been before, and then show me a vista never before dreamt. And so these particle accelerators are creating energy environments that we've never seen before. And under certain levels of energy, matter behaves differently. New kinds of particles show up. Maybe they were predicted, maybe they were not. One of the biggest challenges in modern day astrophysics is, what is dark matter? There's some stuff out there in the universe that has gravity, but we don't know what it is. It doesn't interact with our matter, and it's 5 times of it than it is of us out there in the universe. So we're the small fraction of stuff we don't know what it is. I got this whole chapter, there's a whole place in here. You want to learn about the depth of our ignorance, well, you go in here, you'll find it. Here, the book, that is, for the radio crowd, who doesn't see my gesticulations towards the book.
Yeah.
And so, sorry everyone out there in radio land. So if I walk to the left, I have to like do footsteps, right? Like they used to do. So, where was I again before I interrupted myself?
Somebody on the right, please.
That's their big chance. A particle accelerator, you're at the limits. Oh, so it may be that there's a new class of particle that has no interest in interacting with the kinds of particles we're made of. But we're not in the regime to find those particles. This kind of particle accelerator at Geneva will be testing energy levels that may reveal this class of particles, supersymmetric particles, that's what they're called. And they would have the properties of the dark matter, what we're calling dark matter in the universe. And then we'd have the solution to that, and we go on to the next problem. But dark matter's been a mystery for 80 years, a cosmic mystery. Right. But that's one of many. And string theorists are trying to eke out something to help them out. And I still think they need even higher energies than what are now planned.
Okay, we have time for one more question, and several people have asked questions around this general area. Is what you see the most interesting and proximate questions that are being worked on by astrophysicists and cosmologists in today's research?
Oh, there's no question about it. If you were to rank the problems, the unknowns, you want to start with the ones that make you feel most stupid, okay? So, for example, we know the universe is expanding. That was discovered by Hubble, the man, back in the 1920s. And, okay, we can understand that gravity, it should be slowing down, though, because the gravity operates to bring it back. Observations in the 1990s showed that we're not only expanding, we're accelerating. There's some mysterious pressure in the universe operating opposite that of gravity. Turns out this opposite gravity, this inverse term, it's kind of anti-gravity, though has science 5 baggage that I don't want to bring into this. It's more a pressure opposite that of gravity. There's actually a term in Einstein's equations that allows this. So the physics doesn't have trouble, the Einstein physics doesn't have trouble with this term. It's trying to understand what's causing it. We have no way to understand how this can be. So we call it the dark energy problem. Not that we know that we don't know what it is. It's just a placeholder. The dark energy problem. I put that #1 list. There are missions being planned at NASA right now to try to further probe the properties of the dark energy. Next is the dark matter problem. That's been with us for 80 years. We still don't know what it is. It's less of a big problem as dark energy. Dark energy is like 75% of everything in the universe is dark energy. 85% of the rest of what's in the universe is dark matter. 4% is us. Electrons, protons, neutrons, and light. Everywhere in the universe, that adds up to 4% of everything that's out there. So we don't know what 96% of the universe is. We can measure it. We know where it is. We know how it operates. We don't know what it is. And so these are top questions. Next, and I'll end with the last one, the next one is simply understanding how to go from inanimate chemistry to animate chemistry. Complex chemistry such that you will have a collection of molecules that, after 3 billion years, can pose the question, how did I come to be this complex chemistry of molecules? And it's been said that the atom is the universe's way of posing questions about itself, because the atoms become molecules, become life. And so those are the most profound in the search for life. Find another life form, then compare it. Imagine what you'd learn. Maybe it's made of DNA. That'd be kind of interesting. Maybe DNA is inevitable. Or maybe nature's cleverer than that and comes up with a host of ways to do it. You go to Mars, find out it's DNA. By the way, we learned that there are bacteria that stow away on rocks that can be thrust off of planets after getting hit by an asteroid, move through interplanetary space and land on other objects. Bacteria that are hardy, that can be freeze-dried and reconstituted and radiation and frozen and squeezed. We got those on Earth. Suppose Mars, which we know was once wet, had that whole flora and fauna. And now they're all gone, but maybe Mars got hit and one of these rocks with bacteria on it came to Earth, seeding Earth with life. It's called panspermia. It's a real idea with real physics to support the idea. If that's the case, that means all of us are descendants of Martians. Which has got to be better than venereals. Yeah, okay. Thank you. Thank you for your time. Thank you for that warm welcome. It's good to be back in this visit to San Francisco. I'm told the sun was out a couple of days ago. Is that right? The rain is, plants need rain more than we do. Thanks for coming out for this. I'm here to just kind of talk about the universe, but through the lens, I'm restricted to the universe in my subject matter. In Death by Black Hole, first, I couldn't resist that title. There's a chapter in here with that title, and that chapter bears that title because it's a complete discussion of how you die when you fall into a black hole. And when I think of black holes, I think of sort of the adult counterpart to what, as a kid, would be T-Rex, because every kid loves T-Rex. But why do they love T-Rex? It's because T-Rex can eat the kid, all right? And you tend to have a deep respect for things that can eat you. So black holes, when you come too close to them, weird things happen to your body. And I'll get back to that in just a few minutes. I'm not going to read from the book because you can just get the book and read the book yourself. So presumably you came to hear me say something differently enlightening or even relatedly enlightening to what's in the book. And so what I'm going to do is, the book is organized into sections with multiple chapters within. I'm going to pick one of the chapters within its section that happen to be one of my favorites, and then I'll just kind of give you some summary points of those chapters, okay? And then, so this will be a sampling of the science that titillates me, but also, this collection is the science that has been most requested by the public. even if I didn't think it was interesting. The public thought it was interesting. I said, well, let me find out why. And part of it was this black hole thing. Everybody wants to know about black holes. If I'm on the plane and someone sees I'm reading some astrophysics literature, say, what do you do? I do astrophysics. First question is, tell me about black holes. Then maybe Search for Life and Big Bang. And I'm trying to think, well, suppose I said I was like, you know, nuclear chemist or particle physicist. That would just end the conversation right there. But they find that I study the universe, and it becomes this very engaged conversation. So there's this appetite for cosmic content for which I see myself as a servant of public interest. And so the material that's in here is the blending of aspects of the universe that I want to bring you to, and aspects of the universe for which I know the public has a deep curiosity to learn more about. And so that's how that goes. And let me lead off with the following datum. There's about 6,500 astrophysicists in the world. It's not very many, actually. It's just, a few thousand.